A programmable logic controller, or PLC, is a small, self-contained, rugged computer designed to control processes and events in an industrial environment. That is, to take over the job previously done with relay logic controllers. There are a number of different types and brands of PLCs. Physically, they range in size from that of a camera to that of a shoebox, and sometimes larger. Wires from switches, sensors, and other input devices are attached directly to the PLC. Wires driving lights, small motors, motor starters, and other devices are also connected directly to the PLC. Each PLC contains a microprocessor that has been programmed to drive the output terminals in a specific manner based on the signals from the input terminals. The PLC program is usually developed on a separate computer using special software provided by the PLC manufacturer. Once the program has been written, it is transferred or downloaded to the PLC. From this point on, the PLC may operate on its own as a completely independent controller. The block diagram for a PLC is shown and includes the fundamental parts found in any microprocessor system, as discussed in Module B earlier in the semester. These major functional blocks are explained next. PLCs are usually powered directly from 120 or 240 volts AC. The power supply converts the AC into DC voltages for the internal microprocessor components. It may also provide the user with a source of reduced voltage to drive switches, small relays, indicator lamps, and the like. The processor is a microprocessor-based CPU, and it is the part of the PLC that is capable of reading and executing the program instructions one by one, such as the rungs of a ladder logic program. The PLC bus are the wires in the backplane of a PLC modular system, which contains the data bus, the address bus, and the control signals. The processor uses the bus to communicate with the modules. The program memory receives and holds the downloaded program instructions from the programming device. If this memory is standard RAM, the program will be lost every time the power is turned off, requiring it to be reloaded. To avoid this bother, the program memory may use an EEPROM, remember, electrically erasable programmable ROM, or a battery backup RAM, both of which are capable of retaining data even when the power is off. Older PLCs used an EEPROM, a UV erasable PROM, to store the program, but this device required a special programming unit that is not part of the PLC system. Data memory is RAM memory used as a scratch pad by the processor to temporarily store internal and external program-generated data. For example, it would store the present status of all switches connected to the input terminals and the value of internal counters and timers. The programming port is an input-output I/O port, and it receives the downloaded program from the programming device, usually a PC. Remember that the PLC does not have an elaborate front panel or a built-in monitor. Thus, to see what the PLC is doing, what's going on inside for debugging and troubleshooting, you must connect it to a PC. The I/O modules, the input-output modules, are interfaces to the outside world. These control ports may be built into the PLC unit, or more typically are packaged as separate plug-in modules, where each module contains a set of ports. The most common type of I/O is called discrete I/O or digital I/O and deals with on-off devices. Discrete input modules connect real-world switches to the PLC and are available for either AC or DC voltages, typically 240 volts AC, 120 volts AC, 24 volts DC, and 5 volts DC. As shown, circuitry within the module converts the switch voltages into a logic voltage for the processor. Notice that an AC switch voltage must first be converted to a DC voltage with a rectifier. Also, an input module will usually include an opto-isolator to prevent possible high voltage spikes from entering the PLC. A typical discrete input module would have 4, 8, or 16 inputs. Discrete output modules provide on-off signals to drive lamps, relays, small motors, motor starters, and other devices. Several types of output ports are available. Triac outputs control AC devices. Transistor switches control DC devices. And relays control AC or DC devices and provides isolation as well. A typical discrete output module would have 4, 8, or 16 outputs. Analog I/O modules allow the PLC to handle analog signals. An analog input module has one or more ADCs, remember analog to digital converters, allowing analog sensors such as temperature to be connected directly to the PLC. Depending on the module, the analog voltage or current is converted into an 8, 12, or 16-bit digital word. An analog output module contains one or more DACs, digital to analog converters, allowing the PLC to provide an analog output, for example, to drive a DC motor at various voltage levels. Specialized modules that perform particular functions are available for many PLCs. Examples include thermocouple module, interfaces a thermocouple to the PLC. Motion control module runs independently to control multi-axis motion in a device such as a robot. Or a communications module which connects a PLC to a network. The PLC evolved as a replacement for hardwired relay logic and was designed to be installed, programmed, used, and maintained by technicians who were familiar with industrial relay and switching circuits. For this reason, manufacturers of PLCs developed a programming language that allows the user to program the desired control logic in the form of a ladder diagram. The ladder diagram may be entered into the system by either drawing it on a PC screen or using a specially adapted switch box called a handheld programmer. If the PC is used, special software must be installed before the ladder diagram can be entered. Assuming that the ladder diagram has been entered into a PC, the next step is to connect the PC to the PLC. In most cases, simply connect the two units with a cable or an interface circuit. A more sophisticated system may have a number of PLCs connected to a single PC on a LAN, or local area network, industrial Ethernet. With this system, the PC can communicate with any PLC on the network. Once connection has been established, the program is downloaded and from the PC into the PLC. With the program loaded, the PLC is ready to operate. And in any real application, the next step is testing and debugging. Testing can be done one of two ways. The total software approach, where the inputs are simulated from the programming terminal PC, or a more real-world approach, where the inputs and outputs are connected to their actual destinations. In either case, the PC screen becomes a window into the workings of the program. If a problem becomes apparent, the program can be corrected immediately, and the testing continued until all bugs are worked out. When the testing is complete, the PC can be disconnected and the PLC will continue to execute its stored program as an independent unit. The PLC accomplishes its job of implementing the ladder logic control program in a typical computer fashion, one step at a time. To see how it does this, let's examine a simple PLC application of turning lamps on and off. Notice that the PLC has one input module and one output module. Two external switches, SW0 and SW1, are connected to the PLC via terminals IN0 and IN1 of the input module. Two terminals of the output module, OUT0 and OUT1, drive two indicator lamps, lamp 0 and lamp 1. The ladder diagram for this application has only two rungs. The top rung will light lamp 0 if both SW0 and SW1 are closed. The bottom rung will light lamp 1 if either SW0 or OUT0 are closed. The OUT0 contacts can be thought of as normally open relay contacts of coil OUT0 in rung 1. Assume that the program has been loaded into the PLC and is residing in the program section of memory. When the PLC is set to run mode, program execution begins. Execution is accomplished as a series of steps, which are repeated over and over. One complete cycle of all these steps is a scan. The steps are as follows. Step 1. The PLC reads in data from the input module and stores the values of all 8 inputs as a word in the input data section of memory. Each bit in the word represents the present status of one external switch. Step 2. The PLC turns its attention to the ladder diagram, starting with the first rung. The first two symbols in the rung are input switches. So the processor reads the status from RAM. It then evaluates the logic indicated by the rung. In this case, SW0 is on and SW1 is off, so OUT0 will not be energized. The status of OUT0 is stored as a 0 bit in the output data section of RAM. Step 3. After completely dealing with the first rung, the PLC turns its attention to the second rung. The status of IN0 and OUT0 are read from the RAM. Using these data, the PLC performs the rung logic, which is an OR operation between IN0 and OUT0. Recall that OUT0 is the output of the top rung and is presently off. In this case, because SW0 is on, OUT1 will be energized, and this result is stored as a 1 bit in the output section of the RAM. This completes action on the second rung. If there were more rungs, each would be evaluated in sequence until all had been executed. Step 4 is a final action of the scan. The updated output data in RAM are sent to the output module, causing all 8 output terminals to be updated at once. In this case, lamp 0 would be off and lamp 1 would be on. Now the PLC will go into a rest state for a few seconds or less until the designated scan time has elapsed, and then the whole process starts over again with step 1. Looking over the process just described, some observations are in order. First, the PLC accomplishes its control mission in the same way that all digital controllers work, by executing a loop, a scan, over and over again, For the PLC, however, the looping action is automatic and does not have to be programmed. For each scan, inputs are read in, outputs are calculated based on the inputs, and then the outputs are sent out to the real world. This means that as much as one scan time delay may be between an input and an output. Such a delay is not present in a true hardwired relay circuit, where the only delay would be the propagation time of the relays. This leads to the second observation. The order of the rungs in the ladder diagram may be important because the rungs are executed sequentially from top to bottom. A final observation of the PLC hardware operation is that, for all practical purposes, it can do many independent control operations at the same time. We have been conditioned to think of a computer as being able to do only one thing at a time, albeit very rapidly. And as we have seen, the PLC does not execute its program one rung at a time. However, each rung is a separate circuit, and each control application, as far as the PLC is concerned, is only a set of rungs. Therefore, you can have one PLC running 3 different control applications at the same time. Each application would have its own assigned I/O terminal and its own set of rungs in the program. Within one scan cycle of the program, the PLC would update the 3 sets of outputs. This is similar to the chess master who plays 3 opponents simultaneously by going down the line, making one move at each board.